So in this section, we finally reached lipid self-assembly. So I want to go through basically what kind of general geometries or shapes these self-assembled lipids can take or form. Then we're going to go through some analysis of some mathematical analysis of how we can predict which types of shapes are going to be formed. Afterwards, we'll do a quick overview of critical micelle concentration, because that will play a key role in what kinds of shapes will be preferred or favorable. And then just some brief fundamentals of lipid self-assembly. So first of all, a quick overview. A micelle or a vesicle can be formed by self-assembly. So that's basically us putting in lipids into a solution and then them wanting to form some sort of enclosed structure so that the hydrophobic tails get away from water. So you have amphiphilic molecules, which are those phospholipid molecules. They have both a hydrophobic and hydrophilic area. The two classes of amphiphiles are phospholipid and strong detergent. And essentially self-assembly can occur at an oil-water interface or emulsion. So an emulsion would basically be something that's cloudy and it's got more of a mixture. This image here actually shows the three main geometrical shapes of lipid structures. So first, you have the bilayer, which we talked so much about in the previous section. Then if you don't have a bilayer and you simply have just one amphiphile, you end up with a micelle. And then if you have a phospholipid with just very widespread tails, then it doesn't make sense that it could even structurally form a micelle or a vesicle with the polar heads outside. The polar heads would have to be inside just because of the individual shapes that are created here. So you end up with something called an H2 phase, which is like an inverted micelle. So just to recap, you have your bilayer micelle and the inverted micelle structures. So we've taken a look at the different types of shapes that lipids can self-assemble into. The question now is, when can they actually assemble into these shapes? So we have to introduce a term called CMC, or critical micelle concentration. So that concentration is going to be the concentration of amphiphiles, or basically lipids with a polar head and nonpolar tail. So however many amphiphiles are required to allow it to assemble into a micelle. So let's say you have 3 of these amphiphiles floating around, and this would be what we would call disordered state of lipids. And maybe at some point you end up with more of these lipids. So increase the number of lipids in the solution so that it becomes more saturated. So maybe at this point you'll have more lipids. So it's still in a disordered state, but there's a higher concentration. And basically at some higher concentration, or once some CMC is reached, so we reach the critical micelle concentration, or a certain number of lipids, then we'll be able to see the formation of a micellar structure. Just drawing this as an example. So in this case, once the CMC is reached, that's when, or that is the minimum number of amphiphiles required to form a micelle. So this is a micellar structure. And then if you have more and more lipids, there are two things that can happen. Number one, you can form the same micellar structure with additional disordered lipids floating around. Or if you have enough of these lipids floating around, or amphiphils floating around, it might form a secondary micellar structure. So the critical micelle concentration would simply be the minimum number of amphiphils that will create one of these micelles. So next, we kind of want to look at some ways to try and quantify what we've just looked at. So I want to introduce a few terms here, or just a couple of important parameters. We want to call n the aggregation number, and we want to call this the concentration of amphiphils in aggregates of some sort of aggregation number. So this has been quite tricky in the past. Essentially what this is saying is for n is the concentration of capital N of a certain aggregation number. So for example, you can have n equals 2, and then when you're taking a look at the concentration of n, it's the concentration of tumors that are present in the system. So let's take a look at a couple of examples. We can have n equals 1, in which case it's simply just one lipid. You can have n equals 8. And in this case, you'd have 1, 2, 3, 4, 5, 6, 7, 8. So this would be n equals 8, and then you can have n equals 15 as another example. So like something like this. So this would be, for each of these, I would be able to figure out the aggregation number for each of the structures I'm looking at, but just from the diagram itself, I can also look at the concentration. So thinking about the concentration of just a 1-mer, so that would be this one, is equal to 1, because I only have one of those. The concentration of an 8-mer, I only have one structure that has 8 lipids together, so it's also 1. And the concentration of my 15-mer is equal to 1 as well. So just keep in mind the main differences between n and after we put in a square bracket to get the concentration of those n-mers. Next, we want to take a look at the entropic chemical potential. So let's first define what this is. The entropic chemical potential is defined as follows. Basically, for each monomer, we can use this. mu1 is equal to mu1 naught plus kBt ln of the concentration of that monomer. So if I want to graphically represent this, I can. So let's just highlight this first. Let's say I have this being my n-mer, and at some point this specific term is simply going to be kBt ln of the concentration of my NMR. So a lot of people have been confused by the two terms the last time I taught it, so hopefully this clears things up. This simply means the concentration of NMRs, which is equal to the number of NMRs for each volume that you're looking at. So what else can we look at here? I'm going to go to the next page and basically present another ratio. If we divide the concentration of NMRs by N, we get something that's called the concentration of amphiphiles in an NMR state. So then our equation for the chemical potential can now be generalized. So we have mu n equals to mu n naught plus kBt over n ln of n over n. So for thermodynamic studies, this is a model that has been used to represent the individual chemical potential of specific NMRs for micelles. Depending on which experiments you apply this to, you'll have to tweak the different terms and also adjust your chemical potential starting point for different situations and scenarios that you look at. So this is the chemical potential of individual amphiphiles in their NMR state. And that's pretty much it. We've been able to come up with some model to represent that. Now we want to take a look at dimerization. So because we are trying to assemble lipids, we basically have to think back to when we looked at polymerization, so basically adding another piece to the chain. So keep in mind, dimerization was essentially A plus B going to C, or vice versa. Which means if you are going to be adding different components together, your chemical potentials will be mu something, and I'll just write this in general. You have this is equal to mu naught plus kBt times the concentration of your NMR. So whatever that N is, it could be Na, Nb, or Nc. So here we can replace that with Ni, where I is equal to A, B, or C. So then looking at this dimerization, what happens in equilibrium? So in equilibrium, you're going to end up with mu A plus mu B is equal to mu C. The chemical potential should be the same on both sides for the reactants and the products. So that if A is equal to B, then you end up with 2 mu A is equal to mu C, and therefore we can equate it to negative epsilon plus kBt ln of C, because that's the individual chemical potential for UC, or mu C. And over here, that is simply mu naught. But we are looking at the dimer. So we know that the concentration here is simply going to be the concentration of our dimer divided by however many molecules there are in one dimer, which is 2. So therefore, I can state the chemical potentials for each of these. You have mu A being equal to basically mu C divided by 2. So mu A is equal to negative epsilon over 2 plus kBt over 2 ln of the concentration of a tumor divided by 2. So let's highlight this as another equation we've been able to derive. So we're still not done yet. Sometimes we really do want to know what the concentration of the N-mers are. So basically, how many micelles do you have in your substance or your solution? So sometimes you want to solve for N, and that means we can say the initial concentrations are 1 naught, which is equal to 1 plus 2 plus all the way up to N. So that basically says these are all of our concentrations of 1 mers, 2 mers, 3 mers, up to N mers, all in your solution. In principle, we want to solve these equations for N. So we're going to start with something we've defined already. So we're going to start with mu1 naught plus kBt ln of 1 is equal to mu n naught plus kBt over n ln of n over n. So what are we exactly solving for? If we were to rearrange and solve for the concentration of n, we get n times the square, not the square root, times concentration of a monomer times E to the mu1 naught minus mu n naught over kBt to the power of n. This is going to tell us the individual concentration of the N-mer based on a micelle model. Okay, so we're now going to look at 2 different cases of what happens if your n is really small and what happens when your n is really big. So as n approaches infinity, so basically you have tons and tons of lipids inside your micelle, so it becomes a fairly large micelle. If that does happen, then you have mu n naught going to this, and it's going to be equal to some kind of constant. And what does this mean? It just means that your chemical potential is just going to reach a constant value or a plateau at some sort of value at some point. Now you have what happens as n, or basically as your concentration of 1 is much less than 1. Basically, the number of 1 mers that you have is just a lot less than 1, or basically it goes to 0. Now if that happens, we can say if 1 is sufficiently small, then the concentration of your n-mers is going to be much less than the concentration of a 1 mer. So what does this even mean? To summarize these findings, the main point I want to stress is that this tells me that the concentration of n-mers, which basically means need more lipids for this, what this is saying is that if I already don't have enough individual monomers of lipids to form a 1 mer, or essentially a 2 mer, or a dimer, or a trimer or something, if I don't have enough lipids to form a good number of dimers and trimers, then there is no way that I'm going to have enough lipids to form an even bigger structure. So, main takeaway point, if you don't have enough lipids for a smaller structure or micelle, then you will surely not have enough to form large n-mer structures. So that part makes sense. If you don't have enough building blocks, you're not going to be able to build bigger pieces or bigger complexes. So then let's circle back to what happens at the CMC. I just want to go through a few things. At the CMC, it's not the concentration of micelles. So last year, or last time I taught this course, there was a lot of confusion with what CMC actually stood for. It is not going to be the concentration of micelles. This is actually going to be your concentration of n-mer. What we want to know is that the CMC is the concentration of amphiphiles that are required to start the formation of micelles. So then for different types of lipid, there's going to be different critical micelle concentrations. So therefore, we must define we must define the starting point or starting threshold for micellar formation for different types of lipids. And a follow-up question would be why? And the why is simply because different lipids or amphiphils will have different shapes and affect the value of N. So one example is having, for example here, I'll draw a quick lipid that kind of looks like this, but maybe we can model it using a triangle, so something that looks kind of like that. So if I were to break this up, pretty bad job. Just something more like that. Okay, so if I have a shape like this, then I draw a triangle around it, or a sector, and I spin it around 360 degrees. It kind of looks to me like I can fit 8 of these lipids so that it forms a micelle. But in some other cases, you might have a larger head and a thinner tail. In that case, you end up with like a wide sector. So this is a very crude drawing, but in this case, this would be more suitable for a former. So it's very important to understand that different types of lipids will have different values of N and therefore have different critical micelle concentrations. So we've talked about meeting the CMC. What happens if we surpass the CMC? So let's quickly draw what happens when we reach CMC. Essentially what's happening is this. You have a couple of lipids, or a few lipids, floating around, and you're going to get, so I have 5 of them here, 1, 2, 3, 4, 5. Okay, let's pretend that's our micelle with some circular shape. We can say an enmer is formed when the CMC is reached. Now what happens when we go beyond the CMC? And so when we go beyond the CMC, a few different things happen. Specifically, we might create a bilayer. So let's say you have tons of these. Many amphiphils. So then the concentration of these amphiphils would be much greater than the CMC. So concentration is going to be greater than CMC. So what would happen here is possibly the formation of, first of all, First of all, we have one layer like this, so it kind of matches this over here. We have an enmer that's formed, but then we have so many more amphiphiles that we can use. So in some cases, you actually end up with 2 layers of lipids. So I've drawn this a little bit too big, so it doesn't really have a good physical representation. But essentially this is your closed lipid bilayer. So in this case, you'd have a closed lipid bilayer, which is also called a liposome. So then I want to put in a little note here that more complex structures can be formed beyond the CMC. So if you're interested in modeling any of these types of lipids or trying to figure out the CMC, that is something that you can try and do for your modeling project. Basically, what other structures can there be with lipids or different types of lipids that have surpassed the CMC?